Good morning, folks. Hope all is well here. I just and took a little bit of a break last night. Decided to come back to it this morning, just so I can be a little bit more fresh for you guys. All right, you're so fresh. All right, he's fresh. He's so fresh. Sorry, I won't start singing hip hop. It's just you don't deserve that kind of thing. You're in good class. Why would I sort of assault you with my lack of hip hop talents? All right, let's get back to hydrohalogenation. All right, so note the temperature used in this reaction. We talked a little bit about it last time in the video. That this is has to be cold in order for this to occur right here, okay? And we will go into why that is when we have the potential for having competition between two mechanisms, all right? Does it matter if this bromine adds to the right or the left side? In this case, it doesn't, but mostly it does, and we will see many examples of that, okay? So hydrohalogenations. Okay, so regiochemistry becomes important for asymmetrical alkenes. Asymmetrical, of course, means one side is different than the other side. For example, here are two sides of an alkene. There's this side here and this side here, and they are very different in terms of their substitution. This guy here is substituted with two methyls. This guy here is substituted with one methyl. All right, and you add your HX across this double bond, which is what we say, and what we say here is that these are vinylic positions, which you might have heard of before, which we talked about in class. And so the question is, where does the X go and where does the H go? Okay, this is two very important, two complementary questions here. Right, the same. They're asking similar things though. All right. So here's the long and short of it. Here we're talking about something called the Markovnikov rule. We'll talk about this for a few slides. The vinylic position currently bears one hydrogen right here. This vinylic position currently bears no hydrogens. This is significant for you to solve the problem. All right. So what you do here is that when you want to know what adds to where, does a hydrogen add to this side or does the bromine add to this side, you always look at what has the least substitution there. In terms of here, this would be the hydrogen. This would be least substituted because it has the least number of carbons on it, or the most number of hydrogens on it. So you want to put the hydrogen from this binary acid on the carbon that already has the more hydrogens on it. It's sort of a nice way to remember it, right? So this hydrogen will go to the carbon that already has the hydrogens on it. So this will go onto this carbon here, giving you this guy here. All right, so one way to look at it, let me just erase that real quick. This can swing on out here, grab that proton like that. That'll kick off that bromine right there, right? And your intermediate will be, right, and I'll draw in the two hydrogens here, and your carbocation, which is of course right over there. All right, and then your bromine here, which is left over, will then attack in to that carbocation right there, giving you the resultant product. So in 1869, Markovnikov showed that in general, hydrogen atoms tend to add to the carbon already bearing more hydrogen atoms. That's one way to put it, all right, which is Markovnikov's rule. All right, so it could also be stated that in general, halogen atoms tend to add to carbons that are more substituted with other carbon groups. That's how he essentially originally said that. All right, it's sort of the other way, the complementary way to say it. The other one goes from the hydrogens perspective. This goes from the halogen perspective. All right, but the whole point is that they'll both give you the same answer. This is a regioselective reaction because only one constitutional isomer is formed in greater quantity than the other. Okay, it's regioselective, not specific, right? Because you'll have a mixture of compounds, but this you have the ability to vary, to have a major product and a minor product. Okay. So if this is the case here, and this is the major product here, what would be the minor product of this guy here? That would be simple. Just put the bromine here on the other side here and the hydrogen on that side. But that would be the very minor product. For some reason, we never even draw the minor product because it's a very minor thing. And if for some reason, when this topic is being taught, we never sort of just even broach the topic of a minor product. But that's just what it is. But we know that it can happen, so we theoretically can't ask that question. All right, so. Let's go into this. So hydrohalogenation, this is what it is. This mechanism is a two-step ionic mechanism. That means ions are formed in the process. All right. So the first step here is, he says, I'm sure he says proton transfer, but we're not doing that because we live in the place where we use more appropriate terminology, and I believe it's called protonation. You protonate one side of this double bond here, right, and then this bromine here will attack in here. So your two steps here are protonation and your nucleophilic attack. The alkene is protonated, then the bromide attacks. All right. So here's the way I've always thought about it, and here's what I call Katz's reinterpretation, because I'm sort of a narcissist, and why can't I put my name on stuff? So let's just look at Katz's reinterpretation of Markovnikov's rule. Here's what I say, and this will get you to the right answer and the major product pretty much every time. All right, instead of saying the hydrogen goes to the carbon with hydrogens already on it, or the bromide goes to the more substituted bromide, let's say this. Let's say the Katz's interpretation is the proton goes to the carbon that will help expose the most stable carbocation. Amen to that, sister. All right, that's the way you'll always get the right answer, right? Let's look at it from my perspective, right? All right, so this double bond here will swing on out. We'll grab that proton right here. All right, and then that will expose either one of two carbocations. It will either expose this carbocation in this respect. Right, so let's just don't worry about that. So this will expose either the secondary carbocation or the tertiary carbocation. All right. So now, based on what we know about carbocation stability from your vast knowledge of SN1 and E1s, which one do you think is going to be more likely, the secondary or the primary? Right. Of course, the tertiary. Right. Sorry. Did I say secondary and primary? Why? I'm sorry. I didn't have nearly enough coffee in me. The tertiary or the secondary. Which one will be more likely? Of course, the tertiary is. Why? The carbocation is just more stable. It's more predominant. It's more long-lived. Why wouldn't this thing be formed formed in greater proportion? All right. So that's why that is. So if you want to look at it from either the Markovnikov perspective or from my perspective, I like my perspective. Of course, I don't like my perspective because it gives you some knowledge. You have to start thinking about the stability of the intermediate very early. And so that's why I like mine, all right? But either way, whatever one works for you, whichever way floats your boat, okay? You can think of it. But I like the fact that this swings on out to expose the most stable carbocation. So try and think of it that way, all right? Okay. So now we've learned about let me just see here real quick. Let me just go back here, all right? So this is Markovnikov's rule, okay? This is Markovnikov's rule, all right? And so this will show you that the hydrogen will go generally to the least substituted and the bromide will go to the more substituted, okay? So now we know that process. All right, so now that we learned the real thing about the Markovnikov's rule, let's try and make it so we can do the opposite if we want to. Why do we want to do the opposite? Because, I don't know, it's the question, or it's what I'm asking you to do, or it's what the exam says, or it's what's on your MCAT, or your dental test, or whatever the hell you're doing with your life. All right, so let's do the other one because it might be an option for you to do the other one, and it's obviously of great synthetic utility. We don't always want to be stuck in one position to only put, the bromide somewhere or the chloride somewhere, right? We want to be able to put things in different places, right? We want to be, again, like I said, control freaks and control the overall mechanism and control the whole scheme here. So let's look at the anti-Markovnikov. Okay, so this is said two different ways. Anti does not refer to anti in terms of Newman's. It just refers to the non-Markovnikov position, okay? All right, so you'll see it if you use your textbook says anti, other textbooks say non. They're used roughly equivalently. So whichever way is good for you, but anti is not anti in terms of Newman. Anti is just the opposite of the regular Markovnikov. All right. So anti or non-Markovnikov products are observed when reactions are performed in the presence of peroxides such as hydrogen peroxide. Your book has this habit of using ROR here, so what is ROR, right? Well, okay, what does hydrogen peroxide look like? Hydrogen peroxide looks like, right? Looks like HOOH, right? But you don't have to use hydrogen peroxide so hydrogen peroxide or peroxides are used in this reaction to affect the anti-Markovnikov addition. But you can also use alkyl peroxide. So alkyl, the R just means your alkyl group. So you can use, ethyl peroxide or terp-butyl peroxide or isopropyl peroxide, right, to do this overall transformation, okay? But you know that I will not allow you to use ROOR or any R groups really as a product or as a starting material or as a reagent. This is a placeholder for a real thing. So if you want to use alkyl peroxides, you must not use this. You must use something like, I don't care, butyl peroxide. That's fun to draw. It looks like toot, right? So like Thomas the Train, kind of a peroxide. Or you can use benzyl peroxide if you want, not benzoyl peroxide. I don't know that would work. It might work, but butyl peroxide also works out very well here. But it's HBr only and some alkyl peroxide or some hydrogen peroxide, all right? That will give you the anti-Markovnikov addition. Practice this with this checkpoint here in your book. Okay, so here's something where I almost never say this, but I have to say it right now. We won't discuss the mechanism of this reaction until chapter 11, okay? Or maybe even a little bit later, okay? This is a radical reaction. It is pretty in-depth. We won't go over it just yet, okay? Don't worry about it just yet. Let's talk about just the transformation. So right now I will ask you to memorize rotely that if you treat an alkene, an asymmetrical alkene with HBr and peroxides, you'll get the anti-Markovnikov addition process, right, in very high yield, okay? Don't worry about the mechanism, just draw it out here. There's no electron pushing here that you have to know. Not yet, but very soon, all right? Hydrogen, okay, so hydrohalogenation, the mechanismos here, okay? HCl and cold, all right? So what do we do here? Very simple stuff here, okay? This guy here. So put your pen right there in the middle of that double bond right there. Swing on out there to that. Grab that proton right there. Break that ionic bond right there. This, of course, is a misnomer. There's no covalent bond there, but we have to push some electrons somewhere. All right. All right. So this is the first two electron pushes that you have to do. You push from electrons from here to the hydrogen, then there, off. Okay. Now we have to draw something. We have to draw this intermediate now, right? Now, this intermediate is now where we have the choice, because here we did not indicate where the carbocation will have to go, right? But we have to decide right now where it has to go. So will the carbocation, based on Katz's reinterpretation or Katz's postulate or whatever the hell we want to call it, where should we put the resulting carbocation, right? If you said secondary position here, go and get yourself another cup of coffee. It's maybe not your time to think about this right now. But if you said tertiary, woohoo, you're all about this. Good job. Okay? And of course, to be clear about it, we will then put the hydrogens. We only put one hydrogen. So let's just star this hydrogen. Let's just say we'll put the star right there, and we'll put this star right there. Seems like it's a pentagram. So maybe this satanic proton here is this satanic proton right here, right? This hydrogen here was already existing. All right, we'll put this right here. All right, and that proton will be different. Let's just say this will be the satanic one. Pentagram. Sorry about you religious folk. So we'll make this one here the holy one. Ooh, here's your crucifix. No, wait a minute. That can't be a plus because it looks like a carbocation. So let's just say this is the peace sign for you peaceniks. Okay, how's that? Here's your peace sign. I'm getting way too into this right now. I'm sorry. I'm making a big mess. All right. So here's your carbocation. Right, and there's your resulting proton. So there's your proton here that you pulled off from this HCl right there, this satanic proton right there. All right, and then you have your carbocation right there. Now we do what's the last step. You take your big old anionic chlorine here, and you attack that carbocation as is, and then you can redraw your final product like that. Okay. Cool stuff here. So what do you see here, right? You see that you have this intermediate here, you have this as a carbocation. And when you form carbocations, what do you think else can happen? You know this answer, right? If you form a carbocation, you also have the susceptibility for carbocation rearrangements. All right. And so if you can rearrange, you will rearrange. All right. All right. Let's see about this problem right here, right? So this is the final product right here, okay? And normally we don't draw the other hydrogens on there, but you can if you'd like to, all right? Okay, so here is your Here's your other thing here, right? And let us draw our arrow from the middle of our double bond here. We're not making any decisions yet to this proton right there. This snaps off like so. Now we have to redraw this beast as is, all right? Right? We don't, nothing happens yet, so we have to redraw everything as is. So draw our wedge bond there, draw our guy here. Now we have to draw our carbocation. Will the carbocation be on the primary position or on the secondary position? Absolutely. It'll be on the secondary position. Okay. All right. So if it's on a secondary position, what can happen here? Well, of course you can, if you have a carbocation, you know, you can make away with your initial addition of your chlorine. If you add your chlorine to this, right, and give you this guy here, this is your darkened bond right here, right? But this would be a minor product. This would be a minor product. Why? Because it's a secondary carbocation. Wouldn't it be much better, right, to just be able to migrate a proton from a tertiary position? Right? That's the sound of apparently a hydride migrating. Okay. All right. You now no longer have your carbocation right there, right? You have now your carbocation right here. But if you have your carbocation right here, do you maintain this stereocenter right here? No, no, you do not. You do not, all right, remember this has one proton here. This is a stereocenter, as you see. This is still a stereocenter, as you see here. This is not a stereocenter, right? Because you have 1, 2, 3, 4, two of the same things on it. So this is not the stereocenter. So as soon as you degenerate, right? As soon as you degrade, as soon as you rip away this hydride here, you have a carbocation here. And now you have lost all stereochemical information. All right. All right. So then what happens there? Then you have now you have this ultra stable carbocation species, which is great because now you can have your chlorine come on in and attack. Now let's attack that chlorine. Now let's have the chlorine attack that carbocation, and let's see what we have, and then let's see what we really have. If we're just looking at it dumbly, we're looking at it with the chlorine just like that, right? But you know that's not what we really have, right? We have this as a generality. We have this in quotes, right? But you know that this bond here is a squiggle bond, right? It could be going in front of you or behind you because the chlorine can attack from the front side of this molecule right here or the back side of the molecule, right? So that would really give us two isomers, wouldn't it? It would give you, and I will just what will I do here for you? I'll just have this guy here going away, this guy here coming out, chlorine right there. This bromide here doesn't change any stereochemistry at all, right? Because it's not involved. That plus, and then let's just draw this guy here with then the chlorine going away. All right, cool. So you have this guy here, but we're not really showing any stereochemistry here. But what your book does and your answer key does a whole lot, which I think is a sort of a good idea. It never tries to let you forget where you're coming from here, right? This guy here and this guy here are two stereoisomers, and they are diastereomers of each other. Why are they diastereomers, not enantiomers? Because this stereocenter does not change, while this one does. So if not all of the stereocenters change, you have a set of diastereomers. This will be roughly, and I'm going to say roughly now, roughly a 1-to-1 mixture. This is going to be roughly a 1-to-1 mixture. All right, and here's what I'm going to ask you. I'm going to ask you, probably on the exam, for those of you who are watching this, who are taking very close note of this, I'm going to ask you during your exam for extra credit points. Why is it roughly 1-to-1, but not equivalent to 1-to-1? One of them is the major product, and one of them is the minor product in some respect. I'd like you to tell me why that is. All right. So on slide 912, here is your hidden Easter egg of extra credit questions, okay? And so that's what I'd like you to tell me. All right, so I will remember to put that on, to put this on your exam, okay? All right, what's next? All right, and so we just talked about this here, right? We just talked about the rearrangements of this hydrohalogenations, okay? And so we talked about when you protonate, when you pull off this proton right there, this guy here swings on out, it gives you, right, this carbocation, which can then arrange from the secondary to a tertiary, the minor product being that, and the major product being that, based on the rearranged product. Okay, and so this is a mixture. So this is something that happens. Of course, it's a rearrangement, but it limits synthetic utility because if you've been coming to my discussions, I also give you like two or 3 minutes, hopefully almost every time, about like why does this reaction suck and why is this one great. And that's just sort of based on my experience in the field and experience in just looking at these reactions for 20 years or so. It's just sort of like, you want reactions that do not give you, a great yield, but a gigantic mixture of products. You would like a reaction to give you, if possible, a single stereoisomer, a single regioisomer, and possibly even lower yield that you can bump up. Because past a certain point, if you have a lower yield, you can always engineer that yield upwards by, affecting the concentration or changing the temperature or doing some stoichiometry work. But if you have a reaction here where you have just multiple isomers, it's going to be hard to sort of suss out what you really want and how to get that. Okay, so that's the kind of thing that you want to really look at. All right. Predict the major products from the reactions below. All right, so you have HCl here, and you have this ring here. Look at this ring fusion here. So far, we don't know anything about the ring fusion, but we do know where that proton is right there. If we just do out the let me draw this out a little bit better here. If we just draw out this reaction mechanism, right? It's nothing too crazy about this. We've done this already for a few slides, so we're pretty good at it already. All right, so there's that. All right, so this guy here happens. All right, so then if you want to draw it out in flatland, we can just draw it this way. If you just want to draw it out in flatland, we can just draw it this way. And the proton here will go, the proton here will go to the carbon that already has the more protons on it already. This will expose a tertiary carbocation right there. And then you have your chlorine that comes in here, attacks right there, and then gives you, again, it's all in flatland, but this is not necessarily the whole point of the problem here, right? So there's your chlorine. And there's your problem here, but it doesn't give you all the information about the problem, because why? You have to know something about you. If I'm drawing this molecule for you in this way, that must mean I care in some respect about the relative stereochemistry about this guy here versus this guy here, because you can get two different diastereomers possibly, right? Two different conformations out of this thing, right? It wouldn't be of course diastereomers, because you'll have, this is all equivalency here, right? But this will affect its conformation, right? So it's not stereoisomers, but they are different. They will affect different conformers. So what do you think your major conformer would be from here, right? What do you think your major conformer would be here? My guess is that if this guy here is already pointing downwards, let's sort of try and keep that pointing downwards if possible. Let me see if I can draw it on the first try and get it right. All right, so there's your hydrogen pointing downwards. All right, good. And let's draw our perfect ring fusion of our ring fusion right there. All right, so this guy here, as you can see, is still pointing downwards, just like that. That one's right there, right? So and this is a very stable system, right? As drawn, this is the transdecalin ring system, right? This is the transdecalin. If this was a hydrogen, this would be transdecalin. It's very stable because this stuff here is going to be in the equatorial position. Both of these carbons here, which are attached to a big bulky ring, are equatorial, right? So what you have here is that you have the ability for the chlorine to attack from the front face of this ring here or from the back face of the ring. If you attack from the top face of this ring here, you will end up getting your major product, right? Which is that guy right there, which is very, very, very stable, right? Which is great. This is the trans HCl and the trans ring fusion, which is great. But what happens if the chlorine attacks from the other side, right? What happens that way? Then you end up making, so you have or. This or, that's a crazy or. I'm drawing on a tab. You know my handwriting's terrible, but I'm drawing on a tablet, so this is crazy. So what happens if the chlorine attacks from the other side? If it attacks from the other side, we can still draw the ring as is, but the ring is going to be really kind of crazy looking, right? Because instead of a trans ring fusion, it'll be a cis ring fusion, and then that might be pretty horrible, right? That means that the ring will be up there like that. The hydrogen will still be down, but then the chlorine will be coming in the equatorial position. This guy here is crazy, right? There's a lot of ring strain here, right? Why? Because this guy here, these hydrogens here, and these hydrogens over here, right? And this whole ring system is going to be sterically involved with this other side of the ring system. So this is sterically not so favored. So this would be the minor isomer, right? This guy here would be the major isomer, right? So how do we draw that? No problem. Burp, 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 burp. There's that, and that would be the mage. Okay, cool. So definitely look at that and make sure that you can sort of rediscern why we can do that, why we're doing that. Follow, so like rewind a little bit and follow this argument if you can, okay, about why this is the major product and this is the minor product. This gives you the more stable overall product because of this ring fusion is in the equatorial position, okay. Hydration, very simple stuff, just like HCl across a double bond and HBr that we did a few slides ago. But here you have hydration, which is adding water across a double bond. So what do you do there? Whenever you see H3O plus, immediately just put down H plus, right? Because it's H3O plus is actually H plus and H2O, right? So that's cool, right? Swing this guy out here. Form your carbocation, right? And then have your water come on in. Attack that carbocation. OH there, plus right there. Don't forget that plus charge right there. But you're not done here, right? Then how do you get rid of this positive charge on the oxygen? You know this. Just have another mole of water come in. Don't have another mole of acid come in because acid don't pull protons. Water, in this case here, does. Why? Because it is the conjugate base. Water is the conjugate base of this, right? So you'll pull off that guy right there. This will swing on back down to oxygen. Everyone's happy. You get your alcohol here. Water gets another proton, so it can make some more sweet H3O plus. Homemade H3O, artisanal, homemade hipster H3O plus. So isn't that fun? You can make your own HCl from this process. All right. The acid catalyst is often shown over the arrow because it is regenerated rather than being a reactant. As we just shown here, we've regenerated H3O plus. All right, nothing big there. Here's another. Here's like the non-insane way of drawing out this reaction mechanism away from my crazy scribbles. All right, here is your hydration mechanism. Proton swings on. So this swings on out, grabs a proton, exposes the most stable carbocation. Water comes in, pulls the proton off of there, exposes your alcohol right there. But let's look at another way to look at this thing. Let's look at different ways to look at this, and maybe even a little more detail. Here's your alkene. Here's your R group right here. R group is some alkyl group here. Your proton here. This this swings on out, grabs this proton, and here is your overall thing that you can form right there. Okay. So the way this is drawn here, it's a little bit confusing because it seems like this water is coming from behind this molecule. All right. So be careful about how this is drawn. Actually, yeah, it's weird. So this water here came from behind this, pushing this R frontwards. All right, but this doesn't really matter right now. This is not a stereocenter at this point, so don't worry about that. All right, but look at this. Look at this guy here, right? Here's your alkene, and even though this is a double bond here, this is showing you that one of the double bonds here has its lone pairs that occupies itself above and below the plane of this bond. This should not be, obviously, should not be a double bond. It should just be a single bond here, and this is the other. This is the pi bond, right? This is the pi bond here, right? This pi bond here swings on out, right? Grabs that proton. This is a sort of a nice way to look at this. So this blob of electron density swings on out, grabs a proton right there. As it swings on out, it exposes. Look at this. Look at this little beautiful charge that's sort of forming. That is the carbocation that's just about to emerge, and pop. Once the stress of this pulling gets too much, it pops off, makes that carbocation right there. Right? Then the water's free to come in and attack that and give you that oxonium ion right here, which then has another water come in. Some books do this. Some books just have the proton collapsing down and giving this pair of electrons down into the water. But I like to have something happen to it. All right, because I'm a results guy, right? Right, and then that happens, and then you form this overall alcohol plus H plus. Well, let's just say H3O plus, right? So that's another way to look at it, okay? Cool stuff. Hydration thermodynamics. If you treat this guy here with dilute sulfuric acid, you will have this Markovnikov addition. Markovnikov addition right here. If you use dilute sulfuric acid and so less sulfuric acid and more water will give you the addition product here. This is the addition. But if you use concentrated sulfuric acid, like very strong acid, and or heat if you'd like to, if you use conc sulfuric from here to here, you get the elimination. So eliminations can be done two ways if you have an alcohol, right? So if you have an alcohol here and you want to eliminate it, you don't necessarily have to use lots of heat if you don't want to. You can just use concentrated sulfuric acid, and then that will give you the eliminated product. Okay, that's all that means. All right, here's something that's also very good too. Okay, so this is again just variations on the Markovnikov, non-Markovnikov situation, right? Let me take a sip of coffee here. That's some good stuff. All right. Because rearrangements often produce a mixture of products, right, which is what we've seen before, the synthetic utility of Markovnikov is limited, as we've seen before. We don't want to have a mixture of regioisomers for that OH. So let's say again, being control freaks that we are, we want to if we want to do a Markovnikov addition, we want to do a Markovnikov addition. Period. End of statement. So what do we do here if we want to have some Markovnikov without rearrangement? We use oxymercuration, demercuration. That means we add something with a mercury and an oxygen in it, and then we remove that thing with the mercury in it, okay? Because we don't want the mercury incorporated into our final product, okay? It's pretty not so wonderful. So the first step here is oxymercuration, demercuration. So the first step here is oxymercuration, wherein you make your initial hydroxy mercuric acetate intermediate. This guy here attaches onto this carbon right here, and it makes sure. So before you get to this, and which we'll show you next slide, this shows you that there is no way that this thing can rearrange, and I'll show you the intermediate that's very responsible for that. And then from there, you have your demercuration, which we use a certain reagent called sodium borohydride to demercurate this whole thing right here. Okay, so let's just show you the details of it. The reagent that you use is called mercuric acetate. It's this guy here, but you can also shorthand it using HgOAc2. It's mercuric acetate, right? But this guy here dissociates into the mercuric cation here and acetate. All right, this is what the acetate looks like here. You've seen this before in acetic acid, in sodium acetate. Okay, this is like, so here is acetic acid, which is the acidic version of this, and if you pull off this proton here, you make the acetate ion. All right, so what happens here? The pi bond here swings on out and grabs that proton grabs that mercury, that mercury cation right there, right? And it forms this mercurinium ion or mercurinium bridge. Okay? So this happens here. It swings on down here. So now let me tell you why this is so important. Notice, so remember from before, if we were to do a Markovnikov addition with HCl and HBr, the proton swings on out and forms a carbocation. That carbocation can rearrange. Why can that carbocation rearrange? It can rearrange because it has the ability to rearrange. It sees maybe other available protons, and it's like, hey, I'm a free carbocation, I'm cool. I can just rearrange because I can just move around. Because I'm a carbocation, I can shift to the next thing. But if you trap that carbocation with another cation like mercury, there is no such problem of that ever happening. All right, so that will not happen. So all you're doing here is trapping this carbocation with a mercury. All right, and when you do that, then you have the availability of now the nucleophile. In this case here, it would probably be water, right? If you want to do the Markovnikov addition, right? It will attack one of two sides of that former double bond. That former double bond. All right. So let's just say the nucleophile here was actually water. All right. It will attack this side here versus this side here. Right. In this case here, it will attack this side versus this side. Why? Why do you think so? Look at what this carbon really is. This carbon really is here. Not counting the mercury. This guy here is a secondary carbon. This guy here is a tertiary carbon. This water, or whatever nucleophile that you want to use, in this case it will be water because we want to do hydration process without rearrangement, right? This water will want to attack this tertiary position because this tertiary position has a more developed partial positive charge. Why does this tertiary position have a partial positive charge? Because it is a tertiary position. It is a very stable potential carbocation. Even though you form this guy here, it doesn't mean that this has no carbocation character to it. No, this has here some delta plus character, right? And this guy here has less than that. This guy here has less than that. All right. So this guy here also has. But I'll draw it small, very small. But this partial charge here is much bigger than that charge right there, because this is a potential tertiary carbocation. This is a potential secondary carbocation. All right. So this guy here will want to be way more stable than this guy here in terms of looking at it like a carbocation, which is how we should look at this. All right. So that's why if you use water here, of course, it will want to attack right there and kick that guy up there like so, and this guy here will give you the water right there. So now all that's left to do is take your sodium borohydride and replace and take this guy here and treat this guy here with borohydride, and this will replace this entire group here with essentially a hydride, right, ion, right, because this is a good source of hydride. We won't do the mechanism. Don't worry about that mechanism. It goes by a free radical mechanism, and I'm not going to hold you responsible for it. It's not the point of this thing. We might touch on it if you really want me to during class, but right now this is not that important, okay? But just know that sodium borohydride does that, okay? So here is the whole reaction setup of this. Mercury acetate and water and sodium borohydride. So you can do out the mechanism from here, but you can tell me why that, and I won't do out the mechanism because we've seen it before. You can always rewind it. So here is your minor product. Here's your major product, right? This is mage. This is mine, right? Because of carbocation rearrangement, you have the secondary, and then it forms to the tertiary. That's why it's the minor and the major product. But look at this, mercuric acetate. Here, the first thing you do is HgOAC, right? And you can just say this guy here. You can swing out here and grab this guy right here. This is a plus charge right there, right? Right, so there's that, right? And then from there, you can just redraw this intermediate, right, as HgOAC. This will now have a positive charge again. It quenches its positive charge if you only have one bond to it. But if it's two bonds to it, going back and forth, it is now going back to being a positive charge there. And now here is your water coming in, and the water is like, do I attack here or do I attack here? Well, if I attack here, does this have as much of a juicy carbocation potentially as this does? Well, this would be, if these were two carbocations, this would be a primary, this would be a secondary. So this positive character with this guy right there is a lot larger. So that water is going to feel this greater partial positive charge right there. So that's where it's indeed going to go. This will swing on over and attack that carbon right there and kick this guy over there like so. And then what you end up with OH there, HG OAC. All right, then from there you can always just have another water, or you know what, hell, even acetate coming, because you have an acetate floating around. So you can have water or acetate floating around. Let's use OAC minus as the base that will pull off that proton, generate some acetic acid. Acetic acid's friendly enough, right? 5% of it in water is vinegar, so it can't be that terrible, right? There's your OH right there. And then HGO OAC. All right, that guy right there. And then from there, all you have to do is at that point just say sodium borohydride, and then we are good to go there. Okay, so don't worry about anything else after that. And then you have this regio specifically. This is your only product that you can possibly make. All right. This is the Markovnikov addition of water across a double bond without rearrangement. So this is 100% drawn like a crazy person. 100%. Jeez, oh, I'm making a complete. This is like a maniac drawing this. Okay, this is 100% regio specificity versus this guy here being 60-40 or whatever it is. Okay, that's what the utility of this guy is here. Okay, so it's really a wonderful little piece of science here. So again, make friends with oxymercuration, demercuration. It will serve you well in your synthetic process here. Okay. And so here is hydroboration oxidation, which we're probably going to, at this point, stop right here, and we will continue this with lecture on Monday. This is a little bit more involved, but we will be able to finish up Chapter 9 hopefully by Wednesday and have that happen. Okay, so remember about that extra credit on that other slide that I showed you. Okay, thank you for your time and attention, and go and take a shower. Jesus. Oh, something smell. Oh, it's probably me. I really should shower more. I don't know that. I guess I have to remove this feather boa, but it brings out something in me. I don't know. Anyway, all right. You guys have a good rest of the whatever the hell it is, and I will see you soon. All right, later on.